Okay, so we're talking about contiguous allocation. And again, contiguous here refers physically contiguous, okay? And so what can you do? Well, let's go back to this relocation register concept. You have base and limit, and and you rely on MMU to help you do this. And so depending on where there's enough chunk of memory, that's your offset, and then you can set the relocation register there. Hardware helps you do the translation, right? And so here, the way it does it is logical address gets issued by your program, comes out of CPU, part of the memory pipeline, and is it less than the limit register? If not, then you have the trap error. If so, you add the relocation register. Why? Because you assume your program starts from 0, so you don't need to check if it's less than 0. And these addresses are treated as unsigned anyway. So if it's a really high address, it's treated as greater. It's never less than 0, right? So your program can have this concept of, okay, I own the entire address space, or from 0 up, and let the MMU take care of relocating my physical address by doing that add in the pipeline. Okay? And multiple partition allocation, we've seen variable size partition and fixed sized. Now, variable size could be more efficient in the sense that you size the partition to a given process need, as needed, but then as processes come and go, they start to leave holes in there, right? And they can be scattered, and then you don't have enough. So what do? Well, several ways. You could say, well, okay, let's basically exit all processes and then combine these and then do it again. Well, that's not very practical because then that is, pretty drastic to have to restart processes, and programs don't like that, right? And then another is to say, well, do you have a way to move the memory around so that I combine all these holes together in one chunk, and then that may be how I'll get them back, right? So let's consider this case. Now you have a case where OS loads in a number of processes. They come and go, and now it's fully utilized as shown on the left. Process 5, 8, and 2. Now process 8 exits, leaves a hole, nice and big hole in there. Process 9 gets started, fits in there, fine. And then process 5 exits. So now you do have free memory, but then it's now divided up. One smaller chunk before, a bigger chunk after. Okay. So this, and then if you want a bigger process, or process 8 to come in again, or another instance of process 8, then guess what? There's enough free memory total, but not enough contiguous to fit process 8 right there, right? That's called fragmentation. So what can you do? Well, so there are different ways, and we'll talk about that. But one key idea, though, is just how do you manage where you allocate. The straightforward way is, well, I just keep going, and then if I find a big enough chunk, I use it there. Well, is that the best way to do it? It may or may not be. So first fit is kind of intuitive, right? Because now I have more processes coming. Okay, let's say not process 8, but maybe there's another process that comes in. Do you put it in the smaller chunk or the bigger chunk here? That's a question. You say, oh, of course, so always put in the smaller chunk. That fits. That's first fit. But why is that actually a better idea? And in fact, there's counter examples where that might actually not be the good idea, right? Well, first fit, that's most intuitive because you scan and then find, oh, first one, that's first hole that's big enough. I put it in there. And then why? Because that's kind of the most straightforward way. If it fits, it works, right? And I don't care if if it's going to leave bigger or smaller holes behind. I take my chances, and I'll deal with it when I have a problem. Now, best fit says, well, that's probably not the best idea. You probably want to look at all the different holes and say, maybe I want to find the smallest hole that fits, right? Why? Because then you still save these big holes for the bigger processes, right? So you hopefully have less waste. But then, is that even the best scheme? It's unclear. And I mean, this does have the effect of producing the smallest leftover hole, but then you end up with lots of small holes if you keep doing that, right? And if you're unlucky, you still have the problem of fragmentation, and it may be even harder. Now, worst fit is kind of counterintuitive. It says, I'm going to find the largest hole possible, and then that's where I'm going to put the process. Say, really? Why would you do that? Well, that's because the leftover hole is the largest. Say, okay, so that means what? That means hopefully, if you have any fragmentation, these are not lots of tiny little holes, but fewer bigger holes, and maybe that's a better idea. All right, so. Okay, you're ahead of me. So first fit is you scan down, and then the chance of you getting the first one, because you don't necessarily have to scan through the entire list of holes, right? So on average, you're likely to find one that fits more quickly. Yes, best fit is, well, this is what the book says. And if you read the book, they actually didn't give a good explanation for this. They just say, generally true. Okay, you kind of take their words for it. My guess is that because you have to do both best fit and worst fit need to go through the entire list. But you could keep them sorted, okay? And for sorting purpose, now best fit, I mean, depending on also your sorting scheme, you could use bucket sort, you could use other sort. And how to say? I think it has to do with the order in which you keep this list sorted, probably. That's my guess. So if you leave the smallest hole behind, then that means if you keep them sorted, you're likely to put them in the higher front part of the sorted list. Worst fit, on the other hand, yes, you may leave the largest leftover hole, but then it tends to be in the middle of your list. And so it takes longer time for you to go into the middle of the list, maintain that sorted list. That would be my interpretation on it. But if you read the book, they actually didn't have detailed explanation on why this is the case. So, but I'm giving you my take on this. Okay. Now, so we have this problem called a fragmentation. That is, there's memory available, but you can't use it for several reasons. And in fact, there's two kinds of fragmentation. One is called external fragmentation, and the other called internal fragmentation. What we've seen so far is what's called external fragmentation. And that happens when you have variable-sized allocation. And to some extent, even if you have fixed size, you could still have a little bit of it. But internal fragmentation is really for fixed-sized, mostly for fixed-sized. And external fragmentation, what does that mean? That means if you look at the total available memory, add up the total available memory, yes, that seems like I should be able to service some requests, but it's all scattered, not one chunk big enough. So let's look at one example. You have a 6K of memory right here. one K is used, next 2K is free. Another K is used, another 2K is free. And then I come in, I want 3K. And it says, well, you got 4K available total, right? And said, no, sorry, I can't give you a 3K because I don't have 3K together, right? So that's an example of external fragmentation. What's internal fragmentation? Internal fragmentation is, well, I'm gonna divide up the memory, and in this case, 8K memory into 2K partitions. So I have 4 partitions, each one 2K, right? And then I have, well, these, so now 4 processes are using. But first process, well, it doesn't use 2K. It uses maybe 1.1K. The next one, 1.2K. Next one, 1.3K. Next one, 1.4K. Now, 4 processes are using. Now, 5th process comes in. Can the 5th process get any? Even though, hey, I'm only using 10K of, no, I'm using 1K of memory. Seems like there, maybe one of them, or this maybe half a K, right? Certainly, this process, some partition is not using its memory, and in fact, its free memory is bigger than the next process that comes in. But is that red process allowed to use that any leftover free memory in an existing process partition? No, not allowed. Why? Because by definition of fixed partition, once you give a partition to a process, it owns that entire partition. Okay? So yes, even though some process is not using its entire partition, you can reuse its internal space to service the request of another one, because you're up against the limit of your multi-programming right here. So it doesn't matter how little or how much memory you can accommodate, in this case, 4 processes. That's it. Okay? And so even though the 5th one comes in and clearly needs a lot less, and clearly some processes internally have available memory, you can make that available to this 5th process, period. Right? So that's called internal fragmentation. So these 2 terms are important. So you make sure you understand what these mean. Right? And now first fit analysis generally has on average about 0.5 n blocks lost due to fragmentation. So that means about like 2/3 used, 1/3 lost due to fragmentation. Right? So that's an issue. So what can you do? Say, couldn't I just move these memories around? I mean, okay, so let's not talk about internal. Let's just talk about external fragmentation, right? Because I can start anywhere I want. And wouldn't it be good if I just move this 1K all the way up to this part? Then I have 4K free together, right? Couldn't I do that? Well, that's a nice idea. If you could do it, great. Certainly, that's one way to do it. But that comes back to the issue of address binding, right? When do you do the binding? If it's done at compile time, sorry, out of question. If it's done at load time, again, out of question, right? Because the loader already fixes the addresses based on the time you load in the executable. But if it's done at execution time, binding done at execution time, you may have a chance, right? So because you can say, well, I can at runtime change the base address register for that process. So I move it, then yeah, I update that register. So the process, of course, gets suspended while the memory is moved. And by the time it gets resumed, didn't know what happens, and suddenly all the registers are done, or all the addresses are still done correctly. Why? Because the program still thinks in terms of its logical address. So 18 is still 18 address. 20 is still 20. All right? No need to update its pointers because any offset is added in by that hardware, right? The relocation register. It's hardware. It's transparent to the program. So now, so if you do binding at execution time, you're in luck. But that just means you're likely to have a chance to do compaction, but it's not always possible. So why? Because sometimes you actually may be using certain things such as I/O buffer, and so that means the I/O may be going on behind your call, right? And so the I/O there, well, when it's OS actually just says, okay, that's the physical memory, and if you have to move OS moves that process's image to a different location. Well, how do you tell the I/O controller, hey, now you could go to this one? That translation is not done to the I/O space. Can't do it, right? And then also, what do you have to do? You may have to copy that entire image to some location, and then put it in there, or depending on the order in which you do memory move. There's usually not a single move instruction on most architectures. So you have to rely on some other library or certain other mechanisms to do the move. And so depending on how you do it, it may be a little tricky. And so there are some schemes where when you have this kind of dependency, right? And also anytime there's memory access not just by you, but by other mechanisms, whether it's I/O or another process that actually makes it their own mapping, you may have to do something clever. So one possible way to do this is this relocation program has to be aware of probably certain structures. You may have to know if some things are direct pointers and others may be indirect pointers. So in that way, and there may be a certain part that can't be moved, and those will be the direct pointers. But indirect pointers can move, so that they can always find the. So they know where to update these direct pointers in a fixed location. But that still gets complicated. So anyway, so compaction, nice idea. You could do it a lot of the times, but anytime you have additional non-standard pattern, then especially like I/O buffer or any shared memory, then you have to be very careful, right? So, so that's compaction, and we'll talk about compaction as a separate topic later for more memory management. Right now, we're not really doing memory management here. There's a separate chapter just on memory management. Okay, so that was for contiguous memory management. Now, non-contiguous memory allocation, or I should say allocation. So non-contiguous, again, here refers to non-contiguous physical memory, okay? And you can do it by segmentation or by paging. And we won't go into segmentation, even though previous edition of the book did. It's really rarely used now. People universally use paging now, so we'll do paging. Yeah. I didn't understand that question, but no, you would treat memory all the same. Yeah. But if you're talking about non-uniform memory architectures, I suppose that, yeah, you could do that, but that's kind of outside the scope of this chapter. Here we assume memory is uniform. Okay. So paging. So what is paging? Paging is a way of organizing the memory in terms of the fixed-sized pages. So as opposed to fixed size partition. So a partition is one that's big enough to fit the entire process. A page is not such a partition. In fact, a partition may be made of multiple pages. Okay, so that way you can avoid both external fragmentation. You still have some internal fragmentation, just as with any fixed allocation scheme. So right now, internal fragmentation is not the internal fragmentation for the entire partition, but for a page, right? Because a page is kind of your minimum unit of memory use as far as the allocation is concerned. But it gives you more flexibility in how memory can be allocated, because physical memory doesn't have to be contiguous. Only your logical memory thinks it's contiguous, but the different pages, depending on which page you're on, can map to different physical called frames. So we don't call physical pages, we call physical frames. So you need to know the term. Frame refers to the physical memory block. A page is a logical memory block, and they should be of the same size. Okay, and these should be size. It's a power of 2. And why? Because that is one way to concatenate the offset within the page, which is the lower address bits, with the higher part of the address, which gets translated from logical address to physical address. Okay, so the translation does only the upper part of the address. The lower part offset within the page, that's just taken and concatenated. Okay, and that's possible only because you do the this as power of 2. Otherwise, you have to do an adder, which takes time and cost. Right, and so this avoids the problem of varying sized memory chunks. And in fact, it's also a good mechanism for supporting shared memory. But in any case, in the program's view, they have one single memory address per process. Okay, and so that's nice. So OS needs to support paging, and OS keeps track of all free frames. So frame again is this basic block of memory unit in physical memory. And so to do this, it needs a data structure, and generally it's called page table, but there's different variations of page table. And page table would be the most straightforward way to do this kind of mapping. Why? Because you're translating from logical address to physical address. So what this table does is a kind of a lookup. I have the page number, which is the upper bits of my logical address. Use that as an index into the page table, and then what do I get? Well, I get the physical frame number. That frame number I take and concatenate with the lower bits of my logical address. Now I have my physical address. So easy, right? And also paging can be used in conjunction with some kind of storage. And this is called demand paging. And demand paging and what's called swapping, sometimes people mix these terms, because swapping used to mean you take the entire process in its image, move it out, save it temporarily on disk, kind of put it in hibernation, and then so that you free up the memory you use for some other thing, then you can bring it back. But then now it's more limited to just its, in the form of these pages. But it's really called demand paging. So and later we'll talk about virtual memory and also demand paging. But in any case, you may have an associated storage device or called backing store. Okay, and most likely your page size is related to the block size or of of your backing store, because like disk, flash memory, what have you, they most likely have their own natural block size. Okay, here's translation scheme, rather straightforward. So address, depending on how big your page is, then you divide up the address into the page number and page offset. So 2 to the power of bits in the page offset should be your page size, right? So, and then anything higher, well, that's your page number. So if you have a page size of 2 to the n, logical address space of 2 to the m, then how many pages do you have? Well, 2 to the power m minus n, right? So, so nothing difficult here, just a basic data structure. And the hardware, what does it have to do? Well, hardware somehow has to have a way to, if you want hardware to do this, has to have access to page table somehow, right? And so assuming you already know your page size, then you determine the relative number of bits in your offset and the page index, and then that page index is indexed into the table and then concatenated with the same the displacement or the offset. Then that's where you get the physical address. You can access that. Okay, so so logically speaking, that's what it takes. And so you can have a logical memory, page 0, 1, 2, 3 in that order, and a separate page table to map them wherever it likes. So then the page 0 may actually map to frame 1, page 1 may map to frame 4, page 2 may map to frame 3, and all that. So they don't have to be contiguous or in any order at all. Just it can do whatever it wants. Okay. And then, yeah, so that's one example. And so what you do is then you, within the page, these are the offsets, and then the same offset within the page is used to offset from the beginning of that frame. So that's straightforward. Now, but you have fragmentation issue, right? Of course, that depends on the page size. If you have a page size of 2K bytes, then and then you process, well, it may take multiple pages, right? And since your minimum allocation is a page, well, hopefully you use up a lot of whole pages and then you have one leftover page, right? And so unlike the fixed partition scheme of contiguous allocation, your partition has to fit the entire process. Here, each process can be scattered over multiple pages and no problem. Okay, and so most likely you'll fully utilize most pages except for one last page, which is less than, it's modulo page size, right? Your process size modulo your page size, whatever remainder is less than the page size, and that's what you'll use. So worst case is what? You have 1 byte left over, and then so you wasted the page size minus 1 byte. That's the worst case waste. And then best case, you don't have any fragmentation. You use it up because it's a power of 2. And so if you just do average, that's about half of your frame size is wasted. Okay. And so if you have a smaller frame size, what happens? Well, that means you need more entries in your page table to track more these smaller pages. But if you have a larger frame size or page size, then you need fewer page table entries, but your fragmentation could be worse because it's depending on the frame size. Half of the frame size is wasted, right? Now, what's the trend? Well, the trend, as you could probably guess, page sizes become bigger over time. Unix, I think, started with half a K, 1K, and then they bumped up to 4K to larger. And Windows 10 can do 4K, actually 2 page sizes, 2K and 2 megabytes. And Linux also can have 4K pages and then really big architecture dependent, huge pages kind of size. You can type that command to find out. Solaris also has two sizes, 4K, 8K and 4 megabyte pages. So now you have these free frames around. So what? And they're okay even if they're not together in physical memory, because it doesn't really matter. If you need more than a page, then the next one goes to a separate page. Then it can be mapped elsewhere. It doesn't have to be right behind or right next to that other physical frame, right? And now, data structure, I mentioned page table. That's the most straightforward way. You may also want, or your OS may also want to keep track of what's called frame table. And what's a frame table? So page table is, you need to maintain one page table per process, okay? And so that, logically speaking, it maps the entire logical memory space for that process to the frames or physical memory. And mapping just means, well, as long as you have a way to determine its mapping, it's okay. But mapping doesn't have to be for the entire space, because some parts may be unused. And in those cases, you may be able to do some optimization and not have just entries just to say they're unused. You may be able to use some length field or other things to indicate they're unused, so you don't have to make the page table too big. But page table size could be an issue. Now, frame table, on the other hand, keeps track of how each physical frame is used. So you have one frame table for the entire system, right? Because it's tracking the status for your physical memory. It says which frames are available, one entry per frame, and then the frame maps to this, minimally this tuple of what page and what process, right? Because from the process, you know that which table to look, and then the page says which entry of that page, that process page table you're talking about. So so even though your OS keeps track of page table, the OS still needs to keep track of a frame table too, just to see how it's used. And later for demand paging, that's even more important, because you may have to page out, page in, and so you still need to know, establish that correspondence. So page table, you can think of it as a straightforward array or an array of structs. Okay? But is it really that obvious? Because if you're not careful, your page table is going to be huge. How big? Well, we'll show you in a little bit. It can be much bigger than you might think. So there's different variations of it. So we're going to talk about different implementations of page table. But commonly you would keep track of at least two registers. One is a pointer to the start of the page table. So page table base register, PTBR, is pointed to the page table in memory. Okay, and page table length register, PTLR, that's the size of page table. Sorry? No, this would be data structure that is accessible to OS. Whether the CPU accesses, that's CPU dependent. But OS certainly has to keep track of this. Okay, so you say, hey, but isn't page table size fixed? I know how much the memory is. I know how many bits in my address. I know how big each page is. So isn't it fixed size? Well, doesn't have to be, especially if a lot of your pages are unused. Okay, because I mean, when's the last time you write a program that uses your entire memory? I couldn't think of one case, right? I mean, yes, I know I have 32-bit address or 64-bit address, but I mean, my computer doesn't even have that much memory to use up entire address space available, right? So oftentimes you can have sparse entries, and that's why your page table doesn't have to be the worst case size. It rarely happens. In fact, if it happens, part brings your processor to a crawl. So it's useful to keep track of the base table length register because it's very likely to be much smaller than its worst case size. And you would like to have some hardware support. Why? Because this is accessed every time. Every memory access, right? Read or write, it has to do that mapping. But then how easy or how difficult is it to provide this kind of support? I mean, does the processor or MMU have to load the entire page table? Well, that page table could be megabytes, or it could be gigabytes, or something even bigger. Can it afford to do that? That gets too expensive, okay? And so what's the solution? Well, solution is, as you can probably guess, some kind of cache. And this cache is called TLB. So, okay? So instead of taking the entire table, the processor just keeps a cache called TLB. TLB stands for Translation Look-Aside Buffer. Okay? And it's like a cache, or another way of saying this is associative memory. What does that mean? That means the memory, in addition to just the data, also you keep track of the tags. A tag is kind of the key. So remember Python key value pair in dictionary, right? You give a key, and then it does the match. Okay, whatever value is associated with the key, that's what you get as part of lookup. And same thing with associative memory. So because it doesn't have the entire entry for the page table, it has to say which entry it is. So basically, it takes those address bits, put them in the tag part, and then it's done by matching, associative matching. Okay, and then of course the lookup value is the value part. Right. So, and that's a way to do fast lookup of the frame number. And how many entries? Typically, I mean, it could be 32 to 64 is typical. Modern ones can go up to 1K entries. And of course, associative memory is not cheap. It's also high power. So that's why you don't keep that many entries. And hopefully you get high enough hits that this is worth it. Okay. And in fact, as processor caches, you probably know, start from single level to 2-level, 3-level, multi-level caches. TLBs are following similar trend as well. You have multi-level TLBs too. Okay, but the good thing though is this is all part of your memory pipeline. So program doesn't even know it exists. The OS, on the other hand, does need to know. The OS has to manage the TLB entries. And why? Because every time there's a TLB miss, OS has to take control and knows where to find that entry, right? And then fills in, updates the TLB. But then what if your TLB is already fully occupied with mappings? Well, just like caches, you got to find a victim, kick them out, and then replace them, all right? Right over them. And this is okay because these page tables are really, they're just cached entries from your page table anyway. So that way, nothing is lost by kicking somebody out. I mean, the worst is next time you access that page, you get a page, the TLB miss, and then OS takes over, reloads it again. But really, it's a matter of looking up, filling in the entries. Okay. Always may have to do a little bit more bookkeeping there, but that's what what it takes. Now, for certain things, OS may want to wire down these entries permanently so they don't get replaced. Right? That may be a good idea, especially if you have something timing critical or performance critical. Okay. Now, TLB. What else is in TLB other than the tag and the frame number? Well, you may also have what's ASID. What's ASID? So AS is address space. Address space ID. Another way to think about this is, okay, address space is assigned to or one-to-one with a process. You can think okay, maybe you could use a process ID for this. Yeah, it could be the case, but ASID may be a slightly different one, but you can, for all practical purposes, think of it as a process ID. So why would you need to store ASID in TLB? Well, you actually don't have to, but imagine this. OS does context switch, right? And when it does a context switch, what happens? Do you keep these TLB entries? Probably shouldn't, right? Because now, well, each process has its own page table. So, and each page table maps the logical addresses differently than another process, right? So if you don't flush this, what happens? You try to access some location, first thing goes to TLB. And what happens if it happens to be a hit? Then it thinks, I'm going to go ahead, but then it's wrong mapping because you're using another process's mapping. That's not good. And worst of all is it may be mapped to the memory. It actually takes you to another process's memory in physical memory, but you're supposed to protect it. Here, you got to protect it somehow, right? But if you don't do anything, then it actually goes ahead and accesses it. You could be reading somebody's secret data. Even if it's garbage to you, you're not getting access to your own data. So that means that would be incorrect. So what can you do? Well, if you don't have the ASID as part of the matching, then you have no choice, but OS has to flush all the cached entries in TLB and then force them to be TLB missed next time you try to access memory, right? And so you context switch, okay, then access memory, TLB miss, OS takes over, fills in the entry. But then it just took you a while to warm up to the TLB entries, right? Because every time you do a miss, OS takes over, that's more time. And so this can be a big performance hit if you have to flush the TLB entry, right? Because then you lose all that locality, even if your cache is all hit. So that's why ASID is kept in there, because it's part of the match. And so that means when you do the attempt to access the memory, not only do you do the translation, so mapping from the page number to frame number, but at the same time, the hardware does the ASID matching. So that means OS also has to load the current process's ASID as part of context switching into MMU. So then every access it checks, am I still being accessed by the same process? It's a match only if the page number matches and ASID matches. Then that's considered a match on a TLB. Otherwise, if only the page number matches and the ASID doesn't match, that means that's somebody else's page table entry. Okay, so you shouldn't use that. So that's very important. So this ensures you can properly protect it rather than let this boundary condition sneak in this incorrect access. That's just not acceptable, right? So this allows you not to flush the TLB entry even on the context switch. Okay, and that can be very helpful. So as associative memory, minimally you have to have the page number, frame number, and possibly the ASID as well. Okay, and so if the tag matches plus ASID and things match, then you return the frame number, just like a dictionary lookup in Python. Otherwise, the OS takes over, looks up the entry from page table, fills it in, retries. Okay, and the page table, paging hardware looks like this. So TLB is part of your MMU. So that's the memory access pipeline. But the page table is not part of your MMU. Okay, this is what the OS has to keep track of. Okay, and the reason is these page tables tend to be big. Okay, even a few page tables, that's going to be easily on the order of megabytes, but you don't necessarily use them that often, or you don't use most of the entries that often. That's why a cache kind of structure makes sense. So yeah, even though it's drawn this way, the page table is not part of the MMU. Okay, it's not part of that memory pipeline. But this is taken from the book anyway. So only the TLB part and this concatenation is the part of MMU. So that does the TLB translates page number to frame number, concatenates with the offset, acts as physical memory. And this is more of a data flow view. So if it's missed, then OS does a page lookup. This is all entirely in software. It writes it in there, and then really the MMU, this is part of the register in MMU, updates the TLB entry by kicking out somebody if necessary, generates that effective address, then retries the memory access with that physical memory. Okay? And there's effective access time, and now this formula actually comes back next chapter. They did do a little calculation without telling you this formula, so I took it from next chapter and put it in here. So, so this effective access time. So there's associated lookup, which takes some epsilon time unit, and a hit ratio, which is denoted alpha. So now you can calculate effective time as 1 plus alpha time, 1 plus epsilon times alpha plus 2 plus epsilon of 1 minus alpha, and so that is what you can use to calculate the effective access time. So if hit rate is 80%, epsilon 20 nanoseconds with TLB, and memory access 10 nanosecond, then your effective access time, work out the formula is 12 nanosecond, just a little bit more than your memory access. But if the hit ratio is high, and that tends to be the case with TLB. Usually you're talking about 98, 99% of hit rate. Then effective access time, in this case, would be just like 10.1 nanoseconds. So slightly more than your access time. So it's totally worth doing. Okay, even if you have to take a hit, you have to take a TLB miss from time to time. So it's a really good idea. Okay, so now in addition to the process or ASID, you may also need to keep additional bits for memory protection. What kind of protection? So it could be, say, read-only restriction, or you want to allow read-write, or you want to allow execute-only, right, without reading. And so these are possible access rights you might also want to put in your page table, and they get loaded into your frame at the time too, and also TLB, so that any attempt to make it access as part of translation also checks it with the access type, so that it can intercept anything that violates it, and then traps to kernel to handle. Another important thing is what's called valid-invalid bit in the page table entry, and that also gets loaded into your TLB. Okay, so that indicates whether the page has been allocated or not. So what would be an example? So we've seen the case dynamic loading, okay, dynamic memory allocation. So that way, because if you haven't brought it, well, really that page is invalid. So anytime you try to access something that hasn't been allocated, you're likely to be doing something buggy, right? And then you want the OS to be able to get a handle of it, and then throw an exception back, or maybe give it to debugger and all that. And so that's where also the page table length register becomes handy, because a lot of times you don't represent those unused entries. So in addition to checking the unused bits, you can also easily check the page table length register to see if it's beyond the length right? If it's beyond the link, that means it couldn't possibly be valid because I don't even have an entry for it, right? So, and no sense having to represent those. So any violation, the MMU intercepts it and then traps the kernel. Okay, so that's where I want to stop, and now